Appreciate the time you took to join us. My name is Ami. I'm the VP of Process and Innovation in Atlantium Technologies. And today we will discuss the implementation of medium pressure UV for total organic compounds for TOC reduction. With me is my colleague Nitzan Vardi. Nitzan is an application engineer in Atlantium.
Hello, everyone.
Hi, Nitzan. We will have approximately 35 minutes presentation, followed by a Q&A session. So please use the Q&A icon on the bottom of the screen as we go along, and we will try to address most or all of the questions. So the agenda for today's webinar, we will mention the latest trend in ultra-pure water UPW treatment, about the pros and cons of conventional methods for lowering TOC to very low levels. I'll be presenting Atlantium technology with respect to our unique lamps for TOC reduction. You'll hear about the HOD technology. HOD stands for hydro-optic disinfection. I will use this word quite a few times during the webinar. After presenting some of our case studies, Nitzan will then present a very interesting validation we did on the performance of the medium pressure UV on TOC reduction for the semiconductor industry. In this validation, we monitored the TOC online in various locations and also assessed the peroxide formation model. We will discuss the special features that the HOD brings to the TOC removal application, and we will also talk about other applications for this segment. And finally, we will have a Q&A session. So again, don't be shy with questions. This session will be very technical, I think more than what we usually do on webinars. Okay, so lately, the growing trend in production of advanced microelectronics and semiconductor has brought the need for a large volume of water with extremely low TOC residuals. The shift from surface, ground, or tap water to alternative water sources, such as wastewater, also resulted in some challenges of taking out specific undesired compounds from the process. A good example I can give here is urea, if municipal wastewater are the source, or IPA, isopropyl alcohol, if the plant is reusing the water within a cycle. Now, I'm quoting from an article that was published lately. The trend of building reclamation plants is no longer a future trend, but rather a response to the challenges of water scarcity and the need for sustainable practices. TSMC's initiative in Arizona is a significant step towards achieving a near zero liquid discharge. So the usage of water sources, of alternative water sources, and zero discharge is already here. In parallel, the thresholds for specific and non-specific TOC are going lower, and it's now easier than before to detect low level of pollutants. The wafers are going smaller and such require high quality ultra-pure water, and the plants are doing internal risk management as such to have a very strict internal regulation and monitoring. The traditional methods are simply not built for this feedstock to produce high quality water in high volumes. The requirement for polished water TOC varies between the type of industry, from approximately 100 ppb, give or take if it's boiler feed water, 10 ppb for photovoltaic and some microelectronics, and finally for semiconductor, it can be as low as 1 ppb and sometimes even lower. So using UV for TOC reduction is not a new technology. It's applied when high intensity UV light is triggered the TOC destruction and molecules deformation, we can call it. And it is done on a polished step to achieve ultra pure water post-RO with low conductivity and low TOC content. This process is usually done without an oxidizer, unlike typical AOP that uses peroxide or ozone together with the UV to create a radical formation and thus remove the pollutants as a secondary pathway. Okay, let's dive a little deeper here. Using a simple block diagram, I want to describe the different processes we are typically installed in. So, wait, I'll do the laser pointer. So, of course, the treatment of choice for the incoming water would be pre-treatment followed by a double pass RO. And this is done to yield water with approximately 500 ppb of TOC. I know that this may sound a bit low for some of you, but this is a typical design value that we usually get from clients. By the way, conductivity, of course, conductivity in UPW is very low, in the ranges of close to zero, but we won't mention conductivity here. We are here to discuss about the TOC. So in most cases for microelectronics industry and solar panel, the requirement for 10 to 20 ppb will be achieved by a polishing step on the RO permeate using a TOC UV, followed by an EDI, mixed bed, or a ion exchange. I will shortly explain why the downstream processes is required here. For now, I will just say Atlantium units are installed in more than 150 sites, only for this type of applications. Sometimes we'll have in most cases, we'll have a UV for disinfection, much smaller UV for disinfection downstream. Now let's look at the right side here for the semicon industry. We often see that the UPW are produced and maintained within a loop. That makes sense, as the quality requirements for the water can tolerate residual organics, and even require sometimes in the sub-ppb ranges, meaning below than less than 1 ppb. So, and these residual organics will show up even in a closed loop when there is no makeup, when the UV is off. And Nitzan will show it later. So the water are being recirculated, and the UV would be similar here. It means TOC UV followed by post-treatment. But the sizing tool that we will use would be slightly different. So the UPW are then used in production for wafer wash and other usages. And the wastewater from production will sometimes be handled separately and sometimes will join other wastewater stream. But eventually, if you look at the right side here, this is what we often see, that the HOD UV is used to protect the filter, basically the sensors in the effluent line. And there are many, many sensors on the effluent line to measure the effluent quality. So this is for discharge. And on the left side here, this is reuse back to the process, back to the ultrapure water loop. In reuse, we have similar HOD units, only now we have to make those as AOP UV, using an oxidizer such as hydrogen peroxide or ozone. And this is because now the water are not typical RO permeate like we've seen before. They may contain residual of IPA or chloroform. So to conclude this slide, this nice slide, let's say we can call it a one-pass UPW loop, discharge and reuse. And if you ever visited a site with UV4 TOC reduction, you probably saw something like this. Traditionally, the market was using low-pressure UV lamps. These are the systems with many lamps and cables, as you can see here. The low-pressure UV have a small emission at the 185 nanometer. So I'm sure that some of you have heard about the 185. These are also called 185 lamps. We are offering the medium pressure UV with the VUV lamps. That means vacuum UV, that also have the emission at the 185 nanometer. So this is how it looks like. And there are many differences between these two technologies, the medium pressure and the low pressure UV, even though both are called the UV. So I won't elaborate here, but in a nutshell, the HOD medium pressure UV has 10 to 15 times less lamps than the conventional low pressure UV. And the emission spectra is different. So here we can see the emission spectra for both lamps, showing a relative intensity, relative radiance versus the wavelengths. So on the left side, this is a low pressure lamp. This is a monochromatic technology. It means it has a strong emission at 254 nanometer And in the case that TOC reduction application is required, they will also have a small emission at the 185 nanometer where the water photolysis can occur. The medium pressure UV lamps on the right side have an emission spectrum from approximately 200 to 400 nanometers. And the red color here shows our unique VUV lamp that emits also below the 200 and down to 180 nanometer. And why is it important? Because one should take into account that TOC removal using UV has three main mechanisms. The first one is hydroxyl radical formation in the 180 to 200 nanometer range. These are radicals that are formed from the water and destroy the TOC by a secondary pathway. The second, and this is quite unique to medium pressure UV when comparing to low pressure, is direct photolysis, okay, of specific bonds within the TOC in a primary pathway as they absorb wavelengths between in between 200 to 400 nanometer. For example, I can give here a amino acid, amino groups, carboxylic group, a single and double carbon bond, nitrogen hydrogen bond, and so on. The third mechanism, and to my opinion the most important one, is ionization or polarization of the organic matter. So some small molecular weight TOC that already passed the RO membrane because they were not charged, and now when passing through the high intensity UV have some electrical charge and can now be removed by the downstream EDI, mixed bed, or ion exchange. And this is why the UV and the downstream equipment goes as like a bundle. It's a combined process. And this is also why the TOC should be measured downstream to the EDI, for example, and not downstream to the UV. But note that if we shut off the UV, and we will see it later, we will see the TOC will rise at the outlet of the EDI. And also you will see that some organics, we characterized it, some organics are fully oxidized to CO2 and H2O, and some are removed by the downstream process. So after going through some of the fundamentals, let's look at some of the references we have on removing organics worldwide. Okay, when we first started using the medium pressure UV for TOC reduction a decade ago, the solar panel manufacturers in India were open for the adoption of this new technology. And luckily for us and for them, they were very happy with this new technology. And I think we had no client that looked back at the old method. And so each client who started purchasing the HOD units that you are seeing here for his plant eventually kept on purchasing in other sites or with the expansion of the existing site. The shiny blue screen here is Atlantium controller. So here we can see 5 systems, 6-inch, 3 lamps in each, that handles approximately 100 cubic meter per hour with redundancy. So 1 or 2 systems here are redundant, and the effluent quality is 20 ppb TOC. Again, showing another installation in Asia. Pay attention to the EDI here that is downstream to the UV. So here we can count 6 Atlantium HOD systems. And it's easy to see what we discussed a few slides ago, that we have 3 UV for TOC reduction, vertical, you can see it in close-up here. And downstream to it are the EDI units. And then downstream, before production, we will have the UV for disinfection, much smaller UV again. This is from a large manufacturer in the semicon industry, where we installed dozens of systems. The black boxes that you see mounted on the wall are in fact ballast module. So each lamp has a dedicated ballast module. So just imagine how it will look like if you need 10 times the lamps. And if you notice, all units here are installed vertically. So each Atlantium unit can be installed horizontally or vertically. And most clients that have some concern with footprint are choosing to go vertical. This one is from UK. In this case, the application is not TOC removal, it's chlorine photolysis, and it is done pre-RO. And this is for the pharma industry, so our solution is not only for electronics and not only for the RO permeate. Another reason I'm showing this case is that because we had so many installations of pre-RO dechlorination, large systems, and so we decided to make smaller systems for disinfection to protect the downstream RO membrane. And this is because of the feedback that we got from clients saying that the UV was not only knocking down the chlorine, but also results in better membrane performance. So if we have time in the end of the webinar, I will show a case on RO protection. Okay, this case I'm showing here. It's not a standard TOC reduction. This is a photolysis process, direct photolysis, for NDMA removal. So now we're looking at one TOC, which is NDMA. And the reason I chose to show this case is the fact that we were able to reach a very, very low concentration, 2 nanograms per liter here, when the inlet is very high in the ranges of 10,000 nanograms per liter. So it's a good example how the UV can deal with high flow rate. In this case, it was 1500 GPM, give or take, and reach a very low concentration in the outlet. And I think what allows us to do so is the geometry and the design of Atlantium systems, where we have internal reflection of the light within the reactor. And without going into details, in simple words, I can say we are mixing the light within the reactor and not mixing the water in illuminated chamber. So that prevents the escape routes that may occur in different designs. Again, an installation TOC for 20 ppb. This time it's horizontal. Now maintaining the 10 to 20 ppb is very standard in our installation. I want to show us a screenshot from a site. Here it was 5 ppb in black, and in red is the flow rate, and the time span here is 5 days. For the sub ppb TOC, we wanted to validate our technology. It required a special lab that operates in clean room conditions, and I will let Nitzan elaborate on this. So Nitzan, the stage is yours.
Thank you, Ami. Hello, everyone. I'm Nitzan. Very happy to be here and appreciate everyone who took the time to join us. I'll present our TOC reduction validation, or since we already knew we can reduce TOC levels, I would say, as Ami mentioned, sub-ppb TOC reduction validation, as it was mostly to test our HOD VUV ability to reduce it to that level and comply with semiconductor industry demands. So the validation took place in Minnesota in the CTA labs, which, just on a side note, I guess some of you might be familiar with Gary and his team, and they were just extremely professional. It was probably the best place to have that validation. So what we had was a circulation loop of 1 cubic meter tank of water from the primary treatment of polished RO ultrapure water, going through alternating UV technology. So once through low pressure UV, it was a 4 lamps unit of standard low pressure UV, and once with the Atlantium medium pressure HOD VUV. We had our RZ104 unit with 1 lamp operating at 40% power, meaning 400 watts. So just to be clear, each time only 1 UV was operating. After the UV, we had ion exchange resins, which Ami explained the importance of having downstream to the UV, and then ultrafiltration before consumption for lab purposes and going back to the tank. During the test, we measured hydrogen peroxide and TOC levels at one sampling point, going back and forth every 4 hours from upstream to downstream to the operating UV. The objective was first to reduce TOC levels to 0.2 ppb, which is the minimal detection level, and second, to keep it at that level over time. As we will shortly see, TOC was constantly building up in the loop with new makeup water flowing in when needed, and from leaching from polymers throughout the pipeworks. Peroxide was measured as well because we know residuals of it decrease ultrapure water quality and can reduce yield. And so we wanted to compare residual peroxide formation between the two UV technologies. Here we can see some pictures of the lab and instruments used for the test. So on the left is the standard low pressure UV, 4 lamps that they use regularly. In the middle are the ion exchange resins, and on the right is our RZ104 with 1 lamp mounted on a mobile skid that was assembled for this test and for some other pilots as well. And now for the interesting part. So here are the results. In this figure, we can see the concentration level in ppb over a span of 72 hours. The blue line is for the TOC levels, the yellow line is the total carbon, and the red line is the difference, which is the inorganic carbon, primarily carbon dioxide. And this is all with our RZ104 on 40% power. So on the first section, first 24 hours, the UV was off. That was to enable the TOC build up to a level of over 2 ppb. And then it alternates every 4 hours between out of the HOD VUV and into it. The local peaks you can see in the TOC are from makeup water coming in to replace the water for sampling or for lab uses. Those peaks are reoccurring during the entire test span, as you can see, as makeup water were constantly introduced into the loop. And during the first 24 hours with the HOD VUV off, we can see that the TOC is constantly on the rise, even between those makeup peaks. That is due to leaching from polymers throughout the pipeworks. And so we can see that even in a complete closed loop, without treatment, TOC will always increase. And then just as we turn on the HOD, we can see a dramatic drop of TOC levels from more than 2 ppb all the way down to 0.2 ppb within less than 4 hours. We can see that drop obviously in a lower scale, but we can see it in every transition from in to out of the UV. So here, for example, here as well, and again in every transition. And based on that, we got to a range of 20 to 25% TOC reduction within a single HOD VUV pass. Over time, we can see that 40% power was sufficient to reduce TOC levels to 0.2 ppb and stabilize it. This might be a little easier to see in the next slide. So here we can see, we can focus on one transition and see how TOC level drops and stabilizes while measuring continuously out of the UV. In this figure, we can see again the concentration level, this time over a span of 6 hours, 2 hours with lamp off and 4 hours with the lamp on at 40% power. Sampling out of the HOD VUV. Here, black is the TOC, red is the inorganic carbon, and green is the sum of both, with a pink line marking the activation of the HOD VUV on 40% power. Zooming in like this makes it much easier to see the first pass effect and the TOC reduction all the way down to 0.2 ppb. But I actually want to focus on the inorganic carbon, so the red line, in which we can see very interestingly, actually, a significant rise. That rise indicates a full oxidation process, meaning converting TOC components into harmless carbon dioxide and water, which offers distinct operational and quality advantages. We didn't really expect the full oxidation to be that significant, and seeing it at 40% power made us curious about how applying more UV power would affect this process. So here in the added figures, they're the same, but in the middle, the RZ104 lamp is on 70% power, and on the right, it's on 100% power, meaning 1 kilowatt. Now, when looking at the effect of TOC removal with applying different lamp power, we see not only that TOC drops to the detection level of 0.2 ppb faster, as you can see with the light blue arrow, but we also see that the step of inorganic carbon is higher as well. So this is a very nice way to see that higher power is correlated with higher level of full oxidation to carbon dioxide and water. And this can also impact the downstream resin by extending the throughput of the resin, meaning there will be more volume going through the resin before it needs regeneration. Going forward, so another part of the test was measuring peroxide formation. If with the TOC levels we wanted to show we can achieve the same results as low pressure UV, when it comes to residual peroxide, we wanted to show we can do even better. While peroxide is important for the TOC reduction process, residual peroxide lowers water purity and harms yield. Low pressure UV relies only on hydroxyl radicals formation to reduce TOC, and a byproduct of that is relatively high concentrations of peroxide as well. Our medium pressure VUV, as Ami described earlier, relies on 3 different mechanisms for TOC reduction, allowing us to achieve the same TOC reduction while producing significantly less residual peroxide. Let's go over the results to support that claim. So in this table, we can see results from 4 tests with low pressure, 2 control tests with no UV at all, and 2 tests with the HOD VUV. So in every 2 following rows, we can see 2 results of peroxide concentration measured upstream to the UV, followed by 2 results measured downstream to it, with the 4th column showing the average of every 2 samplings, and the 5th column showing the difference between inlet and outlet of the UV. So we can see the low pressure UV generates 2 ppb of peroxide on average on a single pass. The control tests come to show that the only source of peroxide in the water is the UV. So as you can see, with no UV at all, peroxide concentration stays the same. And establishing that, we can now see that medium pressure VUV generates only 0.4 ppb of peroxide on average. We also wanted to validate our low peroxide generation by normalizing it to the power invested in the UV. So here we can see peroxide generation and electrical energy per order, or EED, meaning the power invested to remove the amount of TOC in 1 cubic meter. And on the last column, the peroxide generation per EED. So we compared the RZ104 on 40% power on the first row and on 100% power to the low pressure unit on the third row. And looking at normalized power, we can see that at 40% power, we generate more than 10 times lower peroxide per kilowatt invested, while achieving the same TOC reduction results. And even at 100% power, applying more than double the power, we still got 30% lower peroxide formation per power invested than the low pressure unit. As I mentioned before, we did expect having better results for peroxide formation with our HOD VUV, and here's the answer why. So in this figure, the y-axis is intensity or absorbance, and the x-axis is the wavelength in nanometers. In red, we can see the hydrogen peroxide absorption spectrum. The black line is the low pressure UV lamp emissions, having emissions only at 185 and 254 nanometer. And the blue line is our medium pressure VUV lamps emissions, having the entire UV spectrum starting at 185 nanometer. While the highest absorption level of peroxide is at 185 nanometer, it is still very sensitive in a spectrum of up to about 220 nanometer, which makes the medium pressure VUV much more effective at reducing it. And so peroxide reduction is actually another application that we can do with our VUV systems. And to sum up our sub-PPV validation process and results, so I want to go over the advantages of medium pressure VUV for TOC reduction in the semiconductor industry. So first and foremost, TOC reduction results. We have shown we can stabilize TOC levels at 0.2 ppb and keep it over time. We have shown we can convert most TOC to carbon dioxide, achieving full oxidation of TOC. And we have shown we generate extremely low level of residual peroxide. And we can do all that with a very low number of lamps, which makes operation and maintenance procedures accurate, comfortable, and much easier. So that was my part, and I'll pass it on back to Ami to showcase some more relevant applications.
Thank you, Nitzan, for presenting these fundamental results. I think that it's really not common to see the process in such high resolution as you showed, and thank you for that. Let's see what additional application we can offer for this segment. Some of these applications I didn't mention before in the process flow diagram. Okay, RO protection. Now I can talk for hours about RO protection. This is really my favorite application here, but to make a long story short, and during recent years and after extensive research, we began implementing a novel application of using the HOD UV prior to an RO membrane in order to improve the membrane performance, and more specifically, to extend the time between RO CIPs and the filter's replacements event. In the case you are seeing here, this is from a manufacturer in the semicon industry that was using massive amounts of biocide on the wastewater. It was wastewater that contained a lot of ammonia. And it was installed after filtration, before the pH adjustment and the RO membranes. So 60, I'll do the laser pointer, 60 cubic meter per hour here. And the client was able to have better performance with only a fraction of the amount of biocide that was used prior to the installation. Moreover, when the HOD system went into maintenance, the RO performance was declining again. So the savings here was not only direct savings from less biocide, but also it made the RO brine treatment much more effective, as now it had much less biocides in it. Similar to RO protection, we have applications for biofouling prevention on the filters and the sensors that are located on the effluent line. Okay, so the effluent line is typically monitored much more extensively than in municipal wastewater systems or even in industrial systems, because of the environmental compliance. So clients that are experiencing here that post the HOD UV installation, they are seeing reliable sensors reading, reduced false alarms, and lower maintenance burden here. So to some of you who attended last week's webinar, it will look familiar. Atlantium has partnered with Inspired Solution, a USA-based company, to advance the treatment and destruction of PFAS through innovative photochemical reduction process, not oxidation, but reduction process. And if you want to listen to last week's webinar, you're welcome to contact us. I believe that there is a recording on the YouTube channel. But similar in concept to PFAS destruction, lately we're engaged in many trials for ARP. So unlike AOP, which is advanced oxidation process, ARP is advanced reduction with electron donor instead of a radical donor. And this is done to remove oxidized pollutant, such as PFAS, but also can be applied to chlorate, nitrate, and many more. So using the medium pressure polychromatic wavelengths, we are trying some types of electron donors to generate highly reactive species capable of breaking down these oxidized compounds. So stay tuned for it, because it's a novel application. It's very interesting. Okay, before we move to the Q&A, some key takeaways here. So we discussed about the growing need for high quality UPW in large volumes. the HOD technology is superior for TOC reduction in performance, monitoring, and also OpEx. Yes, OpEx in this webinar, unlike in previous webinars, we didn't go over all the fundamentals of the technology, but you are more than welcome to challenge us about any of these statements. I did ROI calculations many times, and I guarantee we can show almost for any case. The HOD is validated for reaching the sub-ppb levels of TOC while minimizing the risk of peroxide formation. Low number of lamps, direct photolysis. I think I said it all. Thank you so much for attending here. Let's take some questions in the time we have left here. Okay, so some of them were same. We will share the recordings. I believe someone was asking if it can be retrofit into an existing facility. Of course, and we did it quite a few times of retrofitting the technology to an existing conventional treatment. Would system for TOC have different type of lamp compared to disinfection? Absolutely. In most cases, we will use the VUV, the vacuum UV lamps that also emits in the lower wavelengths of 180, 185. What is the required energy for the process? It's in the ranges of 0.1 kilowatt per cubic meter per 1 order of magnitude of removal. How do we prove it works on our water chemistry before committing? You mean how can we give the guarantee? So in most applications where we are seeing a double pass RO going to the plant, the water chemistry is not surprising for us, and we can guarantee results for it. In some cases where special pollutants are required to be removed, urea, IPA, chloroform, whatever, we will do some testing. We will examine the water matrix. We will examine the absorbance spectrum of the pollutant, and we will, if needed, we will perform a pilot. How does performance hold up when the feed TOC flow or UVT fluctuate? Okay, so the system is well monitored. Again, we didn't go over the fundamentals of the technology, but the controller, it's a very user-friendly controller, and it can react to changes in the UVT, in the flow rate, and it can adjust the power to whatever changes that may occur. So we have a set point we can do it for dose, for power, and we have a set point that reacts to the changes in the water. What lamps does Atlantium use? No mercury, correct? These are a medium pressure UV with some mercury in the lamp, as all UVs are. Typical TOC influent levels, it depends on the industry, as I said before. For the microelectronics and for the inlet, let's say the one pass application, it can be between 200 ppb to a little over 1 ppm of TOC. And for the loop, for the UPW loop, it can be as low as 5 ppb to be reduced to the levels of 1 ppb. How should be measured TOC levels after UV or after EDI ion exchange? It said basically it should be measured after the EDI, because this is, as I said, this is a bundle process here, and EDI is doing the absorption, let's call it, the resin is doing the absorption of the newly charged molecules that passed through the UV. In Nitzan, when Nitzan showed the trial, we placed the TOC monitor in the outlet of the UV because we wanted to see what is going on in this point that it is rarely being looked. And we found out, as Nitzan showed, that we are achieving very nice amounts of full oxidation that is not required to be removed by the EDI or mixed bed. It can be removed by the degas process. Okay, guys, I'm sorry, we have many more questions, more than 30, but the time is ran out, and we'll be happy to take these questions offline. So again, thank you very much for joining us, and thank you.